All right, hello everybody. This video is going over the AP Chemistry 1.7 on periodic table trends. Today we're looking at how the periodic table is set up and why we see certain patterns or trends in atomic properties. So the table is organized based on electron configurations, which is basically how electrons fill into shells and sublevels. Because of this organization, we can explain properties like ionization energy, atomic size, ionic size, electron affinity, and electronegativity. All of these trends come back to a few key ideas: where the element sits on the table, Coulomb's law, the shell model, and then the concept of shielding and effective nuclear charge. The really useful part is that these patterns repeat in a predictable way, and that means if we don't have exact data for an element, we can still make a pretty good prediction just by looking at its position on the periodic table. The periodic table is organized to show patterns and trends in the properties of elements. However, in AP Chemistry, it's not enough to just memorize a trend. You actually have to understand why that trend happens. So when we talk about things like ionization energy or atomic radius, don't just say it increases across a period. On the actual exam, that's not going to be a full answer. You have to explain the reason, like increased nuclear charge or shielding or electron configurations, the things that actually cause the trend. And always remember, trends are the observation, but explanations are what actually are going to earn you points. So group 1 are the alkali metals. They all have an electron configuration ending in S1. They tend to lose that one electron to form a 1+ ion, and they're extremely reactive. In fact, their reactivity is going to increase as you move down the group because those valence electrons are moving farther away from the nucleus, so they are easier to remove than if they were closer. Then we have group 2 alkaline earth metals. Those end in S2 if we're talking about electron configuration. They usually lose both of those electrons to form 2+ ions. They are reactive as well, but not as reactive as group 1 elements. Group 17 are the halogens. They end in S2P5. They just need one more electron to fill their outer shell, so they tend to gain an electron to form a -1 ion. They are also extremely reactive, and their reactivity actually increases as you move up the group, which is opposite of the alkali metals. And it's kind of a similar explanation for our halogens. They want to gain that final electron, and as you move up the group, those electrons are closer to the nucleus, which makes a stronger pull. And then finally, we have group 18, which are the noble gases. They have completely filled outer shells, and because of that, it takes an enormous amount of energy to change them. So they're mostly inert, meaning very unreactive. Atomic radius is the distance from the nucleus of the atom to its outermost or valence electrons. When you move across a period from left to right, the atomic radius is going to get smaller. That's because as you move from left to right, you're not adding any shells, however, you are adding protons. And when you increase the positivity of the nucleus, it's going to bring those outermost electrons closer to the nucleus, making the radius smaller. And then when you move down a group, the atomic radius is going to get larger. That's because you are adding more occupied shells as you go down. So the electrons are farther from the nucleus, even though the nuclear charge is also increasing. All right, so let's do a visual representation of a cation. So let's choose lithium. Lithium has 3 protons in its nucleus, and then it has 3 electrons in its electron cloud. We know in the first energy level that can only house 2 electrons, and then the third electron is in the 2s sublevel, or the second energy level. Now, we already talked about in the previous slide that when it becomes an ion, it loses its outermost electron and decreases in radius, and that is because it is losing an entire energy level. So here, if we have lithium become lithium plus 1, that means it lost its outermost electron, and it now only has 1 occupied energy level. So this is lithium with a positive 1 charge. Now let's do a visual of an anion. So let's do fluorine. So fluorine has 9 electrons and 9 protons. So we have 9 protons in the nucleus. Then in the electron cloud, we have 9 electrons. So 2 in the first energy level. Then we have our 2s electrons. And then we have 5 2p electrons. So 1, 2, 3, 4, 5. So this is a neutral atom of fluorine. And when we add an electron, nothing is changing between its protons and electrons in terms of the nucleus having more of a grip on those electrons. What's actually happening is when you add this electron here, there is greater repulsion between all the electrons, and that's going to increase the radius of the atom or the ion. Electronegativity is how strongly an atom's nucleus can pull on the electrons of another atom in a bond. So as you move across a period, electronegativity is going to increase because the nuclear charge is going to get stronger and the atoms are even smaller. So the nucleus has a stronger pull on those bonding electrons. And then as you move down a group, electronegativity is going to decrease. That's because atoms are getting bigger, so the nucleus is farther away from those bonding electrons, which means the pull is not as strong. Ionization energy is the energy needed to remove an electron from an atom. So since atoms can have more than 1 valence electron, we'll be talking about first ionization energy and second ionization energy, and you can continue as long as you have valence electrons. So across a period, ionization energy is going to increase. That's because the atoms are smaller, so the nucleus pulls more strongly on those electrons. And that stronger attraction makes it harder to remove a valence electron, so more energy is required. And then as you go down a group, ionization energy will decrease because atoms have more electron shells, so those valence electrons are further away from the nucleus, which means they are less tightly held, making them easier to remove. So let's talk about ionization energies that can be given to you on the AP exam. So this is an example problem. It says using the ionization energies given below, determine the number of valence electrons this element has. So when we are given a question like this, I want you to look for the largest jump in ionization energies. So since it requires more energy to remove a core electron or a full octet of electrons, the ionization energy is going to increase tremendously. So looking at this set of ionization energies, 1, 2, 3, and 4, we can see that the largest jump is going to be between ionization energy 2 and ionization energy 3. Now that large jump in the data between the second and third ionization energy shows us that it was relatively easy to remove the first and second electron, but really difficult to remove the third. So then we can kind of assume that that third electron is in a new shell, which is closer to the nucleus, which means it's harder to remove and takes more energy. So let's go ahead and visualize that. All right, so what this data is showing us is that we have an atom. Its first electron did not require much energy to remove. So this is this outermost electron. It only took 500 kilojoules per mole to remove that electron. The next one took a little bit more energy to remove. So this is here, our second electron. Then you can see we had a very big jump in ionization energy. That's because we now have a full octet of electrons, which means they are harder to remove, and on top of that, they are closer to the nucleus. So because we are now losing one of these electrons here, it's going to be a much bigger ionization energy than the previous. Electron affinity is the energy change when an atom gains an electron. So usually the first electron affinity is going to be exothermic, which means energy is released. And when energy is released, values are going to be negative. So across a period left to right, electron affinity values become more negative. That means atoms release more energy when they gain an electron because the stronger nuclear charge is going to pull that electron in more tightly. And then down a group, electron affinity values are going to become less negative because the atoms are larger, so the nucleus is farther away from that added electron, and less energy is going to be released. So why are the electron affinity values for group 17 elements higher than those of group 16 elements? And the answer to that question is since group 17 elements have more protons, the Coulombic attraction when adding the electron is going to be greater. And I want you to take a look at the group 17 element data. You'll see that fluorine has a less first electron affinity than chlorine. That's because with fluorine, it's only in the second energy level. There's no D or F sublevel to go into. So because of that, when there are electrons added into fluorine, there's just a ton of repulsion going on. So it actually has a lower electron affinity value than chlorine. Consider the following successive ionization energies of elements X and Y. In which group is X likely to be found? So looking at X, we can see we have a first ionization energy of 513, and then we go up an extreme amount to 7,298. So our biggest jump is going to be between the first and second ionization energies, which tells us that we only have one valence electron. And our group 1 elements is where they have one valence electron, so we're going to assume that X is in group 1. And then B says, which group is Y likely to be found? If we're looking at the ionization energy for Y, we notice a large jump between the second and the third ionization energy, which means we're going to assume it has 2 valence electrons, and our group 2 elements have 2 valence electrons. And then C says there are only 3 ionization energies listed for X, suggests a reason. Well, our first reason, at least my first thought process, is that there's only 3 electrons. So if you wrote that there's only 3 electrons, that would be a perfect answer. You can also tell just how high those second and third ionization energies are, and that's because they are right next to the nucleus, so it's going to take a lot of energy to remove those. And if you have time, I would love for you to pause this video and try to figure this one out on your own, and then start it back up and I will talk you through it. So the first thing I'm going to do when I'm getting a question like this is just look at where these elements are on my periodic table. So I have argon, I have potassium, I have calcium, I have sulfur, and I have chlorine. So I look at these and they're all very close to each other, and when you actually add or remove the electrons, they're all going to have the exact same electron configuration as argon. So starting with argon, argon does not have a charge, it's just its regular element, and that has 18 electrons. Then we have K+, Potassium had 19 electrons, but it lost one, so it also has 18 electrons. Calcium as an ion had 20 electrons, but it lost 2, so it also has 18 electrons. I hope we know where we're going for this with this. Sulfur 2- had 16 electrons, but it gained 2, so it also has 18 electrons. And then chlorine with a negative charge had 17, but that negative charge means it added 1 electron, so it also has 18 electrons. Now I want to take a quick moment to teach you a new vocabulary word, and that is isoelectronic. Now what isoelectronic means is it has the same electron configuration or the same number of electrons. So all of these ions here with argon are isoelectronic because they all have the same electron configuration as argon. Now let's get back to the question. It says arrange the following in order of increasing size. So we know from this lesson that as you increase nuclear charge, you are going to decrease the size of the atom because you are now pulling those electrons closer to the nucleus, which decreases its size. So what we want to look at here is our highest number of protons and our lowest number of protons, and then we can find the trend within that. So calcium has the most amount of protons. It has 20 protons, which means calcium is going to be the smallest of them all. Then we go to potassium with 19 protons. That's going to be a little bit bigger than our calcium ion. Then we go to our neutral element of argon. I'm so sorry, that's supposed to say protons. So argon will be our neutral baseline here. Then we have chlorine with 17 protons. And then our largest with the least amount of protons is going to be our sulfur ion. And that would be our answer. All right, I hope this video helped you with our 1.7 lesson in AP Chemistry. If you have any questions at all, please do not hesitate to ask. I'm always here to answer your questions. Have a great day. Bye.